Good afternoon, engineering fundamentals students. In my first video, the lesson was about the pure capacitive circuit. In my second video, I'm going to explain you the behavior of inductive circuits. This is my topic. You can see here, behavior of a pure inductive circuit. Here also we have two cases. Behavior of a pure inductive circuit at a DC power source and behavior at an AC power source, like in the previous video. Here also you can see two circuits. One is connected with a DC power source, or simply we call the battery, and then in the second circuit, inductor is connected with an AC power source. Right? Now I am going to discuss with you first this first case. That means behavior of a pure inductive circuit at a DC power source. Right? Here this inductor is connected with this DC power source through a simple switch. Right? What I am going to do here is at t equals 0, that means at time equals 0, I close this switch. Right? Then let's see the current variation of this inductor with respect to time. You can see the graph here. I take the current through the inductor as IL and the voltage developed across the inductor as VL. Right? So let's see the current variation first. This is my current variation with respect to time. You can see here the current is gradually increasing through the inductor like this. Right? I take the maximum value as the Imax. The reason for this graph is the inductor initially opposes the flow of current. That's why we receive this kind of a graph. Right? If we plot the current voltage variation, that means VL across the inductor with respect to the time, you can see this graph here. Initial voltage will be the supply voltage, which is E. Then current, the voltage is gradually decreasing, and the final voltage of the inductor will be 0. Right? So you can note 2 points here. At the initial voltage, that means at E, the current through the inductor is 0, and then at 0 inductor voltage, the current through the inductor will be maximum. Here maximum voltage 0 volts. Here voltage is E volts or maximum. Right? At the maximum inductor voltage, the current through the inductor is 0. Right? Now let's move to the second case. That means the behavior of a pure inductive circuit at an AC power source. Right? Here also I close the switch at t equals 0, and then I plot this graph. That means the current variation and the voltage variation of this inductor by following our first case, right? The nature of the input voltage of this circuit is sinusoidal. We take that as V in, right? Here you can see the graph, and then with respect to this input voltage, right? Or then we can write this V in as the VL, because this inductor directly receives the supply voltage through this switch, right? So we can write V equals VL here, right? Then with respect to this inductor voltage variation, we can plot the current variation of the inductor, right? Now let's move to the first case, that means the DC case, right? Here you can note here, at the maximum inductor voltage, the current through the inductor was 0. Here you can see the maximum value. At the maximum value, inductor current is 0. Right? Then at the 0 inductor voltage, the current will be maximum. Right? So at 0 inductor voltage, current will be maximum. I mark that value somewhere here. Right? Then I can plot this graph by following this sinusoidal manner. Right? Then I complete this graph by following this inductor voltage pattern. Right? Let's mark this as the inductor current, IL. Right? Here you can see here there is a phase displacement between the inductor voltage and the inductor current, right? Let's mark first this x-axis or the angle axis, 0 degrees, then 90 degrees, 180 degrees, 270 degrees, 360 degrees, like that. You can mark 90 by 90, right? Here we can say here the inductor current starts after 90 degrees. That means the inductor current is lagging. So we can write here the inductor current lags the inductor voltage by 90 degrees, right? We can write that point here, the inductor current lags the inductor voltage, inductor current lags the inductor voltage by 90 degrees, right? This is our final conclusion, right? We can derive this relation by using mathematical concepts, but in this fundamental subject I used a very simple technique to derive this behavior. So you will be able to derive this using mathematics in your third year, but in this first year this knowledge is enough for you, right? I think this lesson is clear to you. We'll meet again in our third video. Thank you.